All right, so welcome back to our off-season programming training. This is the last week of a training session. Not the last week, but the last week of training. And today we're going to be covering our final topic, PathPlanner and Autonomous. So let's look at where we are. So we've come a long way, and in that you've gotten a lot of knowledge that is going to be helpful for this final section. One thing that I should mention about what's happening today is it doesn't actually end today. You're probably going to get some of the stuff done after this, but there's no expectation you get through all of it because there's a lot from today. But hopefully you'll have an understanding from everything you've already learned. So first, many of you are new to FRC, so let's talk about what the autonomous period is. Every year, typically the first 15 seconds of the game is autonomous, meaning that there's no driver, like the driver has to stay behind the computer, and the robot drives itself, does everything itself. And this period is often very beneficial because you can score a lot of points with a rehearsed action of some kind, a lot more than normal. But it's really short, 15 seconds, not very long. So these are the three types of control that we're going to go over today. You've actually already touched the first one and the second one. The third one should be new. So the first one, time-based control. For some of you, you've already made some kind of command that turns the robot a certain number of degrees by setting the speeds of the motors, and that was on a button press. In this case, it would be autonomously, but it works essentially the same way, just driving the motors in order to drive a certain distance forward or to turn a certain amount just based on time. One major disadvantage of this is there is no guarantee that what you're doing is actually going to work. If the voltage in the battery is a little bit different, the surface of the ground is a little bit different, all these things can affect it and make it not work consistently, and you have no way of knowing that it's off. Next, we have PID-based control. So you touched on this last week with limelight control. Basically, what we can do is we can have either the motors go to certain distances or have the robot turn to a certain angle using different sensors like a gyro or encoders, which tell us the positions of the motors. This allows us to control everything more reliably because we actually are correcting for any error that's introduced. But what can happen is if you're making a very long, complex command with curves that might be difficult to create with straight lines and turns, that's when you might want to move away from this. But for simple things, it can work really well. Then finally, PathPlanner. This is a tool, and it's not the end-all, be-all of everything. It's not always the right solution for what you're trying to do, but it can make certain things a lot easier. So with PathPlanner, you can follow complex trajectories, meaning curvy paths that go back and forth and do other things inside of them, and you can make that a lot more easily than you would otherwise. It also takes advantage of all of the sensors you have, so the gyro, which tells you what angle you're facing, the encoders and the motors, and even sometimes vision, depending on the game. So it can be more accurate even than PID sometimes. But it does require the most setup of all of these options, so we're going to be covering that at the end. So this is our only example of time-based control because of how simple it is. You've probably already seen our run commands that do something repeatedly, and then we can use with timeout to end it after a certain amount of time. In this one, since the speeds are the same, it'll drive forward at a certain speed for a certain amount of time. The other one, since the speeds aren't the same, that means it's doing some kind of turn, and then with a shorter timeout. Now this one would go forward and turn, but if you did them the same speed in opposite directions, it would turn in place. Then our commands.sequential is also pretty useful. That simply runs each command in that order that they're given. So that allows us to do one thing, then the next. Next, we're going to look at how we're going to turn using PID. So if you were here for week 3, this should be pretty familiar. It's almost exactly the same as what you already did, just swapping the limelight with the gyro. So first we store the angle we want to turn to. In this case, we're keeping this as a specific angle. So you could turn to an angle relative to where you are right now. In this case, we're not going to. We're going to store a specific angle and turn to that angle so that anytime you do it, it always turns to the same angle. Then we turn the robot in that direction using PID and min speed, which is the same thing we did last time. And finally, once we're within a certain tolerance that we can choose, then we'll stop. So we actually have to set up the gyro because we haven't done this yet. We haven't set up any of these sensors yet in our code. So inside of the drive subsystem, we create a new variable called, it's of type AHRS, and we call it our gyro. The gyro on this robot is called a navx, and that's just one of the types. On our main robot, we have something called a pigeon, but that's the class that we use to create it. Then in the constructor, we simply make a new AHRS. You don't need to give it an ID or anything like that. That's it. Gyro.reset sets it always to 0, just in case there's anything. We always want to just make sure it's starting off at 0, so there's no confusion. Then we also make a quick method here, and that gives us the rotation of the gyro. Now, this rotation 2D type might be a little bit unfamiliar. This is a little bit different from what you've seen before. What it allows you to do is get, it has methods for getting the angle in degrees and radians. So it's pretty convenient for sending angles when you're not sure what the end format's going to be. So then in our command, I'm going to gloss over this because we've already talked about a lot of this in week 3. But we make our PID controller, our min speed, all looks pretty similar. We do store a desired angle. We take in an angle in degrees, but we actually immediately convert it to radians, simply because it's typically more familiar for people to think in degrees, but internally it's easier to use radians. Then we have our continuous input. That just means that it'll always take the shortest path around the circle rather than getting confused and thinking 0 and 360 are different numbers. And then we give ourselves a tolerance. Here we're giving ourselves a tolerance of 0.1 degrees, though you can change that if it doesn't reach that set point, that kind of thing. Then, another difference, we set our set point here instead of 0, like we did with the limelight, where we wanted it to be right on the target. We set our set point as the desired angle. That's in radians again. Then, right here where we give it our measurement to calculate with, we actually get the rotation from the gyro, from our drive subsystem. So we're using that as our reference to know where we are, just from that gyro, and we do it in radians. Pretty much everything else is exactly the same as what it was last time. Next, let's look at how we drive straight. So last time we drove straight using simply going to a certain Y value with the limelight. This is a little bit different. Since we know the value of each motor, how far each motor has turned, we can actually use that to calculate how far we need to go. So we actually store the distance relative to each side. Because let's say I drive that thing around for a while. The distance that each motor has turned is actually different for each motor. So that's going to make it so you can't just set one distance, but we actually make it a certain distance added to the current distance on that motor. Then we drive each side to that specific distance using PID and min speed again. And once both sides are within that tolerance, then we're done and we're at the right spot. So looking at how we do this, primary difference is that there's 2 PID controllers, and we also store 2 targets instead of 1 desired angle. We take in a distance in meters, that's pretty important, and down here we set a tolerance of 3 centimeters, since we're using meters for this. Next, in our initialize, we do this very simple calculation to figure out the angle that we want each side to go to. So we get the left distance from the drive subsystem, and we add our desired distance onto that to give us the target distance that we're trying to go for on that side. Do the same thing for the right, reset the controllers, and set each set point. Then in the rest of this long line is misleading. It's pretty simple. Basically, we add our min speed, and in the PID controller, we give it the measurement of left distance or right distance, and that's it. Then we drive forward, and we are done when both of the controllers are at their set point, meaning that both sides are within that tolerance that we've given them. They're within 3 centimeters. Next, what is PathPlanner and why do we use it? So PathPlanner is a software, it's open source, and it's just one of many tools. Some teams have different solutions to this problem, but for us, this is what we use. So it allows us, whether with tank drive or swerve drive, to follow complex paths which are often required for different things. So for our autos this year, we have complex paths. We have to pick up multiple game pieces. This makes it a lot easier to add curves and introduce these things without having to worry about complex code to follow all of these different paths. So this is what it looks like to create a PathPlanner trajectory. So this is in the app PathPlanner. The rectangles there represent the robot, and this is a graphic of the field. So you can see this is kind of what it looks like to make one of these paths. You can adjust different things to make the path that you want. So now let's look at how we actually can preview what the path is going to look like. So once we preview it, it's faster in the app than this. This is just a weird GIF, but it will play and then replay the robot following that path, or at least what it should look like. Here I've actually plugged in the actual size of the robot, so that's what it would look like on the actual competition field. Okay. So there's two primary things that we need for running PathPlanner in this system. We have odometry and auto builder. So odometry, this is the object that uses the gyroscope information, right, which angle is the robot facing, and the encoders to track the robot's position on the field. So it's not just thinking about how far each wheel has turned or what angle we're facing, but it actually is tracking where the robot physically is on the field. Even if you're turning and doing all kinds of different motion, it still knows the X, Y, and rotation of your robot on the field. Then our auto builder, this is what actually creates the command that the robot uses to follow this path. So we give it a bunch of information about the robot, we give it access to certain methods that allow us to control the robot, and then it spits out a command that actually will follow that path for you. So first let's look at how we set up odometry in the drive subsystem. So we make our differential drive odometry, and we just call that odometry, and differential drive kinematics. Differential drive is just a fancy word for tank drive, pretty much the exact same thing. So I'll go into that in a second. So for our odometry, we give it our initial gyro rotation, the initial motor positions, which in this case are 0. You don't need to put the negative in there, that's just because of the editor. And then new pose 2D. So like rotation 2D, that should be another new term for you. Pose 2D is simply a point on the field. It contains two things, a translation and a rotation. A translation is just an XY coordinate. It's just that. So that could be a translation, that could be a translation. And then for the rotation component of it, that's the angle that the robot's facing. Okay? So the pose just simply represents where is the robot on the field and which way is it turned. So this is saying a new pose 2D like this is empty, meaning it's 0, 0, 0. So it's facing forward and at 0, 0. Then we also make something called kinematics. All this does basically is store the width of our robot. So if you look at it straight on, it's just the width between the wheels on this side and this side. And that tells it how to drive it. That's basically the only thing that really matters with tank drive is how wide it is. You also can consider how long it is as well, but this is what we're going with right now. Then there's a couple of pieces of information that PathPlanner needs to access from the subsystem. So from our odometry, we need to get the pose, right? Because that's updated. And so for PathPlanner to know where it is or where it is relative to where it wants to be, it needs to know where it thinks it is right now. So our getPose method returns the current pose estimate of the robot. Then we also have getRotation there. GetRotation gets the rotation from the pose. So that can be more accurate than just the gyroscope measurement. So because it combines the encoders and the gyroscope to have that estimate. So we typically will get our rotation or its understanding of where it's facing from the pose estimator or the odometry. We also have a couple of convenience methods here. We do need the reset odometry method that will take in a pose, and it just says to the odometry, this is where we actually are. We're not actually at 0, 0, since our auto might start at some other point on the field. This allows us to tell it, hey, we're starting here, not at just the origin, which most autos don't actually start at. Zero pose command, this is optional if you want it. Sometimes it can be helpful to debug and to say, right now I'm resetting the angle that the robot's facing, and to know for sure that that's happening, but that's more of a debugging thing, so you don't actually need to put that in. Then we have some other methods for getting information from the motors, right? So we just got information from the gyro and set up the odometry, so now we're actually going to use the motors. So the motors each have an encoder which has a method called getPosition. And that getPosition method, it returns a certain amount of revolutions, right? So maybe it's turned 1 revolution, the motor has, then that would return 1. So in order to convert this in the end into meters from just how many times the motor has turned, we have a little bit of converting to do. So first we divide by the gear ratio. In this case, it's 10.7 to 1, meaning that for every 10.7 rotations of the motor, the actual wheel turns once. So we divide by that gear ratio to get how many times the wheel has turned. Then we convert that amount of rotations into radians. You could convert it into degrees, but radians has a convenience factor to it, because once we have this in radians, we can actually multiply by the radius of the wheel, and that will give us the total distance that is traveled. So we do that for both of our motors. We also do a similar thing for our wheel speeds. So our wheel speeds, these encoders give us our velocity in RPM, or rotations per minute, or revolutions per minute, doesn't matter. We also divide by the gear ratio here. Then we can convert from RPM to radians per second, and again multiply by wheel radius to get the meters per second rather than the radians per second. Then we also have something called a periodic method. This is kind of like the execute method of a command, where it runs every 20 milliseconds repeatedly. So it means every 20 milliseconds we're updating where the robot understands itself to be using the gyro and encoder data. Next, we also have some constants. These go at the top of your drive subsystem. So for our wheel radius, the wheels have a diameter of 6 inches, so we convert that to meters and divide by 2 to get the radius. Our track width, which we saw earlier that we needed, it's 26 inches, so again we can convert that to meters, and our gear ratio is 10.7 to 1, or just 10.7. So, yeah. Okay, so next, this is how we're going to set up AutoBuilder in our robot container. So if you do recall, there is a method in your robot container called getAutonomous command, and that's why we're putting this also in robot container, so that it can easily access this and generate our auto for us. First, we actually create our AutoBuilder. That specific type up there is the one for tank drive. You would instead put swerve AutoBuilder if you were doing a swerve robot. Then after we create our drive subsystem, we also make our AutoBuilder. These are all pieces of information that it needs. I will go over them in a second, but it's important to know that this is like a one and done kind of thing. Once you have this set up in your code, you typically don't touch it unless you have a couple of values to tune. So while this looks pretty significant, you're not going to have to write it a lot. So it's important to know what components it has, but you don't really have to hold it in your brain after you have it done. So in order to follow this path, the AutoBuilder needs to know, first of all, where is the robot on the field? What's its pose? So if you recall from before, the way you can pretty easily give a method to something, like what we used for our drive command, where we gave it the joystick inputs, we can use that double colon syntax to give it access to that method. So that gives it access to a method that returns the pose of the robot. It also needs to be able to reset the odometry, again, to tell it where the robot is actually on the field, where it's starting the auto, not just always starting at every auto at 0, 0. We also give it a controller. So the controller includes some math that allows it to understand how it can go at a certain speed, turn a certain amount, that kind of thing. And that's built into WPI load. We also give it our kinematics, which again really just stores the track width of the robot, but that helps it understand how to turn it and go at different speeds as well. Then we have our feed forward, which I'll talk about a little bit more in the next slide, but just know we have a couple of sample values in here. Sometimes that requires tweaking. Then we also get our wheel speeds. So this helps PathPlanner to understand how fast the robot's going so that it can make any kinds of corrections if it needs to. We also give it PID constants. So why does it take PID constants? PathPlanner uses PID internally. It doesn't control each motor individually, but what it does is it looks at where the robot is on the field, and then it'll control for the angle and the speed of the robot so that we can correct for any little error in the system. So it is important. That's another thing that we could tune. Next, we have a drive voltage method in the drive subsystem. You probably don't have this right now in your code, but it's actually really similar to what you already have. So our drive percent or drive tank method, right now it has set voltage on each motor and it just multiplies the percent by 12. For this drive voltage method, it's just that, but without multiplying it by 12. So PathPlanner will output voltages and you just take them in and set the motors to go to those voltages. Event map is beyond the scope of what we're covering right now, so we'll ignore that for now. Use alliance color, also not really that important right now. And then finally, we give it our drive subsystem so that it can just add that as a requirement, remember, so it can override the default drive command. So, quick overview of what a simple motor feed forward is. So this is the first feed forward that you're using other than that min speed, which is pretty simple. Basically, these are all terms that represent an understanding of how the robot can move. So our KS term gives us a basic term that tells us how to overcome static friction with the robot. For us, that's not really important right now. It's not going to make that much of a difference, but it can make a difference. And if you're at that point where that's important, there are tools that can help you calculate these different values. But if you're not there, then you don't have to worry about that. And today we are not worrying about that. KV is something that we're going to use today, because KV is what allows our robot to actually go at the speed you tell it to go in Autonomous. So KV, essentially we give it a velocity we're trying to go. We're trying to go a certain number of meters per second, right? We multiply those meters per second by KV and we get a voltage. So it's that relationship between how fast we're trying to go and what to tell the motors to do. Now that's not perfect. So you might be a little bit off. You might not be able to go at the right speed with this. It might be just a little bit off, and your auto would be a little bit off if you can't correct for it. Hence why we have the PID to correct any little error in the system. But this gets us most of the way there. We also have KA. We're not using that today. This is something, again, you can calculate if you are at that point where this is important. And it essentially looks at how much acceleration you're trying to get, and then we'll multiply that by Ka, give you the voltage. So all these things work together to get the desired output without, like before PID. Then to actually run our autos, we have our get autonomous command. You don't have to worry about what that's called, but what this does is we have our auto builder and we call a method called full auto. That means generate everything, do everything for us automatically. Then we load in our path with PathPlanner.load, our load path. We give it a name. In your editor, in the PathPlanner editor, you can give it your path a name. And it's important that you give the same name in here that you actually gave to your path, or else it won't know which one you're using. Then we also have our path constraints. So for each path, you can tell it how fast you want it to go and how much you want it to accelerate during the path. You're not going to want to start at 3 and 3. That's going to be pretty violent, especially since you guys have been driving like pretty slow, just controlled. We don't want to be driving that fast immediately, so maybe 1 and 1 to start with. You can work your way up. Note that as you go faster, it gets harder for the robot to be in control. So if you tell it to go at full speed and full acceleration while it's making maneuvers, it's going to overshoot. no matter what. It's not going to be exactly correct. So you always want to be careful with those speeds. So we got through that pretty quickly. That's pretty good. So let's go over what we're doing for the lab today. So we have 3 sections. There is no requirement for which order you need to do these in, but I would recommend at least doing some PID before you move on to PathPlanner. Some of you have probably already done some of the time-based autos, but probably not the second one. So you can pick and choose which order you want to do these in. I don't expect you to get through all of this today. And even if you do get to PathPlanner, there's a whole lot that you can do with it, and you will only barely touch the surface today if you do get there. So, work your way down. Most of we've already covered some of this. We've already covered some of this last week. So maybe if you get here by the end of the day, at least setting it up, that's good. The goal is that you can keep coming in to practice and working on these further projects with PathPlanner that we have. So there's not going to be any more lessons after this, but that's a good opportunity for you to actually hone your skills and continue practicing once you're at that point. So yeah, if you have any questions, obviously I'm here. I think I might actually also have to write something up on the board that I forgot to put in the presentation, but other than that, I think we're ready to go. So, yeah.